Hello everyone. In this lecture, we will discuss tautology, contradiction, logical equivalence, and logical implication. So we start with tautology. A statement is called a tautology if it is true for all combinations of truth values of the variables included in it, and we denote it by capital T. It means suppose a compound proposition has n variables or n propositions, then it has 2 raised power n different combinations of truth values. So for each of these combinations, if the compound statement is true, then it is a tautology. So for example, look at this P or negation P. So this is a tautology. Now we check, we make truth value or truth table of this one. So look at this here, P negation P or negation P. So P will have two truth values, true and false. So negation P will be false and true. So P or P in both of the cases, because or is there. So if one variable is true, this is true. So in both of the cases, this is true. That's why it is a tautology. Similarly, we may have another example. Now, contradiction. Statement is called a contradiction if it is false for all combinations of truth values of the variables included in it, and we denote it by F. So here, if it is false for all possible combinations, then we say it is a contradiction. An example of this contradiction, a simple example is P and negation P. Now look at this, just make the table of P and negation P. Look at this, if one of the variable is false, then P and negation P, this is also false. So this is the example of contradiction. Similarly, we may have another example. Now a contingency. A statement is called a contingency if it is neither a tautology nor a contradiction. So you may have many other examples. For example, if you make a truth table of P implies Q, then you know that in some of the case, in one case it is true, it is false, and by another cases, in all other cases, it is false. So in the same way, if you write the truth table of P or Q, similarly P and Q. So these are examples of contingency. These are neither tautology nor contradiction. Now logical equivalence. Two propositions are said to be logically equivalent or simply equivalent if both have the same truth values for all combinations of truth values of the variables included in them. So for this we use this symbol. Suppose a compound proposition, say P is here not a single but say a compound proposition, P is equivalent to Q, then we use this symbol to denote the equivalence. Now look at this one example, P implies Q. This is equivalent to negation P or Q. Now to verify whether this is logical equivalence or not, whether these two P implies Q or this one negation P or Q, both these prepositions, compound prepositions have same truth values or not, we can make truth table. So let us make the truth table. Now look at this. So this is P, Q, four combinations are there. So this is P implies Q, in only one case this is false, otherwise it is true. So there is negation P, negation of P, and if you find the negation P or Q, so you will get this truth table. Look at this, true, false, this is true. If one of the variable is true, then it will be true. So if you check this, the value of this column and this column, you will see this is true, true, false, false, true, 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 true. So all these truth values are same for each of these combinations. That's why you can say P implies Q is equivalent to negation P or Q. Now we have proved this logical equivalence. Further, you can use this equivalence as a formula. Now some logical equivalences. These equivalences can be proved using truth tables, and we can use these equivalences as standard ones. Idempotent laws. P or P equivalent to P, P and P equivalent to P. So this is very easy to prove. Next one is commutative law. Commutative law, P and Q. This is equivalent to Q and P. It means we have changed the order. Similarly, you can write it for disjunction also. Now associative law. Associative law, P and Q and R is equal to P and Q. It means first we have calculated P and Q, then R. Here Q and R first, then calculate this with P. So in this way you can change the association. This is associative law. Similarly, you can write it for disjunction. Next one is distributive laws. Distributive law, here disjunction is or is distributive over and, so this equal to P or Q and P or R. Similarly, here this is and is distributive over or. So this can be written as P and Q or P and R. Now domination laws. Look at this P or T, this equivalent to T. You know that if you find the disjunction of two propositions and one of the propositions is true, then it is true. So if you find the disjunction of P with T, so automatically it will be T. Similarly, P and F equal to F, because P and F equal to F, if one of the variable is false, then it is false. Then these are domination laws. Identity laws. P and T is equivalent to P. P and T, look at this, this will depend on P. If P is true, this is true. If P is false, this is false. So therefore P and T, this is equivalent to P. Similarly, P or F, this is equivalent to P, because this will depend on P. If P is true, then this is true. If P is false, this is false. So these are identity laws. Now negation laws. P or P, negation P or negation P, this is equal to, because if this is true, this is false. So P or P, this is true. P and negation P, it means if P is true, this is false. If P is false, this is true. So every time one variable will be false, so this is false. Absorption laws. P and P or Q, this is equal to P. Look at this, this will depend on the value of P, because if P is true, look at this, true and this is true and Q, whatever the value of Q, since it is true, so this will be true. So true and true, this is equal to true. It means this is equal to P. When P is false, so P is false, false and whatever the value of P or Q, this is, because and is there and this is false, then it will equivalent to false. So this is P and P or Q, this depends on P. Whatever the value of Q, every time you will find this this expression has the same values as P. Similarly, you can define P or P and Q, this is equivalent to P. Morgan's law. Negation of P or Q, this is, if you open this negation, this is equivalent to negation P, and this sign will change is and negation Q. Similarly, negation of P and Q, this is equivalent to negation P or negation Q. Double negation law. Negation of negation P, negation of negation P, this is equivalent to P. So these are some logical equivalences. If you need, you can prove using the truth table, and now you can take all these equivalences as standard ones. Now these are some logical equivalences based on conditional and biconditional statements. We have already proved that P implies Q is equivalent to negation P or Q. Similarly, we can prove all these others using truth tables, and now you can consider these as standard equivalences. Now another important aspect is logical implication. We say that a statement P tautologically implies a statement Q, denoted by P double arrows. So this is P tautologically implies Q. If and only if whenever P is true, Q is also true. It means we have to assume that P is true and we have to check that Q must be true. Only then we will say P tautologically implies Q. So if it's so, then in other words, we can say P implies Q is a tautology. So in this way, we can define logical implication. Now look at this example. P and Q tautologically implies P, or you can say P and P and Q tautologically implies Q. We have to assume this one is true. So if it is true, look at this. This is AND P and Q. It means whenever P and Q is true, it means both of the variables P and Q are true. It means if you assume that P and Q is true, it automatically tells you that P is also true. Similarly, if this is true, it means Q is also true. So this is an implication, and you can say P and Q tautologically implies P, or you can say P and Q tautologically implies Q. Similarly, another example, you can say P tautologically implies P or Q, because whenever P is true, P or Q will be automatically true. Similarly, you can say Q tautologically implies P or Q. The same reasoning will be applicable here. Now look at this biconditional. P implies Q. You know that a biconditional is true whenever P is false. It means negation P, whenever negation P is true, this is also true. It means negation P tautologically implies P implies Q. Similarly, you know this biconditional P implies Q is true whenever Q is true. So you can write Q tautologically implies P implies Q, because whenever Q is true, this conditional P conditional Q is also true. So these are some examples of logical implications. Now suppose if we have to prove the logical implication P and Q implies P. So how can we show this? So first way is to construct the truth table. Right here P, Q, P and Q. So this is true, 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 false, 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 true. This is false, false, false and false. So first way, as I told you, this whenever this is true, this must be true. So you have to check the rows where P and Q is true. This left hand side is true. So only one row is there where this is true. So in the same row, this variable P must be true. So here this is only one row where P and Q is true. So here look at this, T is also true. So you can say that in the first row where P and Q is true, P is also true, and this is the only case. Therefore, P and Q tautologically implies P. Now another way, we can make the truth table of P and Q implies P. So if you make this truth table, so look at this P and Q. Now this is a condition, this is a conclusion. So true, true, this is true, false. Condition is false, but conclusion is true. This is true. Both are false. This is true. Again, both are false. This is true. So in all cases, this is true. So you can say P and Q implies P is a tautology. It means P and Q tautologically implies P. So it's your choice whether to show the implication using the first way or using this tautology. Here I have summarized these implications, and these are some other important implications. First one is modus ponens, this is modus tollens, this is hypothetical syllogism, and this is dilemma. So we will use these implications as standard implication, and we can use further for different problems. To prove a logical equivalence or implication, the simple way is to construct a truth table. But in some of the cases, it is asked to prove a logical equivalence or implication without constructing truth table. So in these cases, we will use the standard results which we have shown in previous slides. So we can, with the help of these results or these formulae, we can prove any equivalence or implication without constructing truth table. So here I am going to take two examples. So first one is I have to show this equivalence. So I will start from left hand side. So this is negation P or negation P and Q. So look at this here, this is negation, so I can use De Morgan's law. So this is equivalent to negation P and negation P and Q. So as I have used the De Morgan's law, so I will clarify it using De Morgan's law. Using De Morgan's law. Now look at this again. We can apply this rule. So this is equivalent to negation P and P or negation Q. So again the same rule is used. So you can write in this way. Now this is equivalent to, here I can use distributive law. So if you apply distributive law, this is negation P and P, or negation P and negation Q. Negation P and negation Q. So you can write it using distributive law. Distributive law. Using distributive law. Now this is equivalent to negation P and P. You know, this is negation P and P. This is false. Or negation P and negation Q. So since negation P and P, this is equivalent to F, that is contradiction. So now you know that F or any proposition, this is equivalent to this proposition, because if it is true then this will be true, if it is false this will be false. So this is equivalent to negation P and negation Q. So you can write it, since F or P is equivalent to P. So in this way, this is the right hand side, negation P and negation Q. So in this way, you can prove a logical equivalence without constructing truth table. So you can start from the left hand side, and or you can start right hand side also. Whatever rule you are using, just describe this rule here. So step by step, you can start from left hand side or right hand side, then move to the other hand side. So in this way, you can prove a logical equivalence. Now we have to prove the logical implication, that is negation P implies Q, tautologically implies Q implies P without constructing truth table. Remember one thing, whenever we have to prove logical implication, then we can use logical equivalences as well as standard logical implications, because if suppose A is equivalent to B, it means A tautologically implies B. So whenever A is equivalent to B, you can write it A tautologically implies B, because whenever A is true, B is also true. But whenever A tautologically implies B, you cannot write A is equivalent to B, because whenever A is true, this is true, but whenever A is false, you cannot say whether B is false or not. So from this to this is possible, from this one, from implication to equivalence, this is not possible. So for showing an implication, we can use the standard equivalences and implications both, but for equivalence we will use only standard equivalences. Now we try to solve this. So negation P implies Q. So we can write this as this tautologically implies negation P or Q. Here you can write, since P implies Q, this is equivalent to negation P or Q, because this is equivalent to this one. So this tautologically implies this one. Now you can write it as P and negation Q, since negation of P or Q, this is equivalent to negation P and negation Q. This is De Morgan's law. De Morgan's law. You can simply write using De Morgan's law. Now this is equivalent to P and Q. You know, P and Q tautologically implies Q. Here P and negation Q. So you can write it. This is negation Q. here you can write it. Okay, since P and Q tautologically implies Q. So here if it is negation, then you will write it negation Q. Now you can write it, we have to show that this tautologically implies Q implies P. This is a conditional statement. In this conditional statement, this is condition and this is conclusion. So you know that whenever this condition is false, the, this conditional statement will be true. So whenever this condition Q is false, Q is false means whenever negation Q is true, so this conditional statement will be true. So here this negation Q is true. So directly you can write, if this is true, then this tautologically implies Q implies P. So here you can write since negation P tautologically implies P implies Q. So here it is negation Q. So negation Q tautologically implies Q implies P. So this is the proof without constructing truth table. So I hope that you got the concept of uh, showing equivalence or showing implications without constructing truth table.